Ooh, just before we start, Mike.
Right, here we go then. So last session, did you catch up on that, Roger, by the way?
No, not yet, Mike. No, it's the
No.
first time I've had a breathing space tonight.
Yeah. Last session we looked at the ideal transformer, and we looked at this method of transferring impedances. So tonight what we're going to do is, that was a precursor to us being able to model practical transformers. In the last session we outlined, or I outlined, what assumptions you are making when you called a transformer ideal. And this is how, this first slide is how real transformers differ. We said ideal transformers, the winders had no resistance, or real transformers, the winders do have resistance, because a piece of copper wire has resistance. We said for the ideal transformer that the cores were infinitely permeable. What that means is, as an ideal transformer, that will take as much magnetic field as you want to pump into it. That's not true of real transformers. They have a finite permeability, so you build up a field, but eventually that field won't build up anymore, however much more current you pass through the coil that's making it. Third thing, the flux produced by the primary is not completely captured by the secondary, and vice versa, i.e. for the ideal transformer we assume there's no leakage flux and that they're perfectly linked. Or real transformers aren't. There's leakage flux on both sides, both the primary and secondary side of a real transformer. We said in the ideal transformer that the iron cores were perfect. There's no eddy current or hysteresis losses. Well, in a real transformer, there are eddy currents that flow in the core, despite all the efforts to minimize them, and that there are hysteresis losses. And so what we're going to do is develop a model of a real transformer, and just make another slide and explain what I mean by hysteresis. If we had, if we draw a graph called a BH curve, where B is flux density, and H is applied mag field. That's actually in amp terms. What happens is, when you apply some current to a coil, ideally, if we had an ideal transformer, we'd get a line like this. It would build up for as long as we liked in that direction or the direction, and when the field is taken away, it would go back to zero and back up the other half if we're applying an AC signal. In reality, what happens with a real transformer is that from zero, we apply our first positive cycle, it builds up until it saturates. Yeah. Then, when it falls away, so you take all your current off, it doesn't fall all the way back to zero. You have to apply a certain amount of reverse magnetic force to get it to go back in the other direction, and then it goes down, saturates in the reverse direction, and then again on the next cycle it will do that. You might have seen a BH curve before, you might not, okay, but there's a couple of terms that I'll make you aware of this point, what should I choose? Orange. The force between there and there is called the coercive force. And this point is called residual magnetism. Now, if you, that BH curve, hysteresis curve, is quite narrow. If you have a really wide one, like that, that's bigger hysteresis loss. The smaller and narrower it is, the less hysteresis loss there is. I thought I'd just summarise that term so it weren't left there as a hanging term without you understanding what it meant. Yeah. And what will happen with that is that's causing some of the heat build up in the core because of this loss that you've got in the area of that BH curve. That some of the magnetism to make it reverse in the opposite direction is needed to remove that residual magnetism from the positive half and so on. Right? Because we got a coercive force here as well, and we got a coercive here as well, and a residual magnetism here. All right? Everybody happy?
Yeah, that's good.
Good. Right, so first of all, we're going to look at the ideal transformer and how we can represent the imperfect core. So at the moment, if you look at the diagram, we're considering a transformer where there's nothing connected to the secondary side. Now, if that transformer was ideal, nothing connected to the secondary side, we'd have no current I2, but with I don't know, let's say 600 volts DG connected, we'd have no current in the primary side either. Now on a real transformer, you do get a current flow and it's open circuit. Because this core isn't ideal, i.e. it's not infinitely permeable, that says, should say, not intimately. So that should say infinitely permeable. And there are hysteresis losses, and there are eddy currents that flow in the core, causing it to heat up, power loss. So when we have a real transformer open circuit on the secondary side, there'll be a current flow in the primary, which I've labelled I0. So we've got a current flow up here, IO1, but nothing going into the ideal transformer because there's no current flowing in the secondary. So this IO goes down here, and then that's the total of IM through an inductance and IR through a resistor, RM. Yeah, where those two components represent, the resistance represents the iron loss in heating. That would give us, because it's a resistor, current and voltage in phase, current and voltage in phase, that will give us watts of power loss due to heating. Yeah, and then the XM, the coil, the inductor, represents what's called the magnetizing current. So that's what current is required just to magnetize primary winding. even though there's not a secondary load attached. Okay?
So, how come the little m is used? What does the m signify?
That's that's the field.
Okay.
Yeah. All right. More about that in a minute.
So
yeah.
Yeah.
Yeah. All right.
Yeah.
So, taking a little bit of a closer look at that. If we look at the phasor diagrams, or phasor diagram of these quantities, okay, EG is across the top here, is EG, that's your reference, okay, and the resistor current is in phase with that, there it is, okay, and then IM is an inductor current, so it's 90 degrees via civil, the word we use, inductive circuit, current lags voltage. So that's 90 degrees out of phase with the resistor current. E2, so the secondary voltage will be in phase with the primary voltage. As one goes up, the other goes up, as one comes down, the other comes down. That will always be true. Yeah. The flux represented by this phasor down to here is in phase with the magnetizing current. Okay, so we've got a overall current IO in there, made up of a horizontal component IR and a vertical component IM. Yeah. Okay.
Yeah. Yep.
But there's nothing going in, no current in to the ideal transformer in the middle, because there's no current being drawn from the other side of the ideal transformer on the secondary side. Happy, everyone?
Yeah, fine.
Yeah?
Yep.
Good.
Yeah, so that XM and the RM are just the like the winding resistance and the inductance represented.
That's right. Yeah.
So
yeah, exactly. Well, RM represents the winding resistance, and it'll also take account in terms of the heating of that core, because it's the core's being heated because the winding is getting hot.
Yeah.
And the winding is getting hot because of its resistance. Yeah.
Okay. Yep.
And then XM, the current through there is the current that's flowing to give you the magnetic field in the primary coil.
Okay.
Yeah. All right.
Yep.
Right. So, as we always tend to do, we have a look at a problem. So, a large transformer at no load draws an exciting current of 8 amps. So what that's saying is it's taken 8 amps to excite the core, yeah, in total. When the primary is connected to a 400 volt, 50 hertz source. From a wattmeter test, it is known that the iron losses are equal to 500 watts. So you're going to find, you must calculate the reactive power absorbed by the core, the value of RM and XM, and the value of IR, IM, and the total current IO. Well, actually, in my opinion, IO has been given to you because that's the exciting current.
Will that always be referred to as the exciting current in questions, or?
Not necessarily, no.
Okay.
These particular problems were taken out of a particular book. So where are we going to start with this problem? We've got EG is 400 volts. We'll pull out what we know, yeah?
Yep.
And IO, 8 amps. We don't know nothing about any phase angle with that at the moment, but we know it's 8 amps, yeah? Magnitude.
Mm-hmm.
Yeah.
Mm-hmm.
And P is 500 watts. So this transformer's drawing 8 amps when we connect 400 volts to the primary side. And the power loss on a wattmeter is 500 watts. So the reactive power, as asking for, is find Q.
So if you've done V over I, yeah, would that give you,
If we look at
S, wouldn't it?
Yeah, because we know P.
Yeah.
We want to know Q. Can we find S? S is equal to I times V. Yeah?
I times V, yeah.
8 times 400 equals 3,200
yeah.
VA. Yeah?
Yeah.
All right?
Uh-huh.
So now we know that and that.
Cool.
We can find Q, can't we? Therefore, Q is equal to square root of S squared minus P squared root 3,200 squared minus 500 squared equals.
So I get 3,161.
3,160 var. Yeah.
Yeah.
Everybody happy with that and up with that? Yeah.
Mm-hmm.
So that's part A. How can we find the value of RM and XM?
You not need to find the currents first before you found that, or
Remember that Q and P are powers, and there are a number of formulae for power.
yeah. So, what is there? There's V squared over R. Is that one of the? That's one of the. Yeah.
Yeah.
So you could.
Well, you can get the IR even easier than that. Because if you think about the diagram, which we didn't draw, you've got your generator.
Yeah.
And that's got 400 volts. And that's connected directly across that resistor. Yeah.
Yeah.
They're in parallel. So you got 400 volts across that resistor.
Yeah. So yeah.
Yeah. And anyway, I'm looking for R, not IR, aren't I?
Oh yeah. There we are.
Sorry, P is equal to, we can do P is equal to E squared over R. Yeah. Therefore, R equals E squared over P. Isn't that not?
Yeah.
Yeah. So it's 400 squared
400 over 500. So I got 320. Let me just check first to make sure it's in brackets. Yeah, 320 ohms.
320 ohms. Yeah. And then we can do Q is equal to E squared over XM. Therefore, XM is equal to E squared over Q, which is 400 squared over 3160.
So I've got 50.6. So should we go 51? Or well, no, 50.6 is the same figure, I suppose.
Is it 50.66666? Because I've got 50.7.
I've got 50.6329, so that would just stay as 50.6.
We don't worry about 0.1 of an ohm really anyway, it's not much, is it? Okay. So that's found the value of RM and XM. Okay. Now we want IR. So this is part C. IR, how can we find that?
So now you have the resistance for each one, or
you got the resistance of the resistor, And you got the reactance of the reactor, yeah?
Yeah.
It's
So
going to
you
be
could
E
do E over
R.
RM.
I got 1.25.
Yep.
Yep.
Mm-hmm.
Agreed.
Yep.
Yeah.
And the angle on that, for reference, is 0, isn't it? Because it's in phase.
Yeah.
Yep.
Yep.
And then IM is E over XM. Yep.
Yep.
450.6 equals
Equals 7.91 is what I've got.
7.9 will do. Angle associated with that inductor current?
That'll be 90. Would that mean minus 90?
Magnitude minus 90. Yep. Inductive current
Yeah.
lags voltage by 90 degrees.
Yeah.
Yeah.
Civil. Yeah.
So IO is IR plus IM. Agreed?
Yep.
So
he's
1.25 as 1.25 plus 0J for the IR bit,
Yeah.
plus 0 minus 7.9 J for the inductive part. Don't need, because the angles are 0, 90 degrees, we don't need a calculator to make that
No.
shouldn't do anyway. So therefore IO
Yeah. So I got 8 amps.
IO equals 1.25 minus 7.9 J. Convert into polar. You got what? 8 amps?
8 amps, and then the angle is minus 81 degrees.
Minus 81 degrees. Exactly what I've got. Everybody follow that okay?
Yep.
Yeah?
Yeah, fine.
Good. Right. In your tutorial questions this week, the first 2 questions are on transformers without no secondary connected. So can I suggest that you will leave the room running, so I'm here to help. I'll have a go at those 2 questions. 1 and 2.
Okie doke.
Yeah.
And you. Yep.
I'll pause the recording for now. All right. So the last thing that you need is nominal rating 100 kVA. Yeah. Everybody got that down?
Yeah. Yep.
Right.
Yep. KVA. So anything which is nominal is on the nameplate.
Yeah, that's what that would be on. Sorry.
To get back.
Yeah, of course, Ben. Yeah, sorry, I didn't
Sorry.
wait for you to say yes.
I'm waiting. Yeah, that's fine.
Okay, Lewis. Yep, good. Warren.
Yeah, good.
Right. So what we're going to do is find I, the transformer ratio, I, B, full load, current, and value of per resistance load that would draw this current. So let's talk about the secondary, by the way.
So would that be Z or is that different from Z?
Yeah, I put Z because you should do. I'm just representing the general load on the diagram, yeah. So because that's AC, we should say as an impedance load, but I've made the load resistive.
Okay.
Yeah, that makes the calculations less complex at this stage. Yeah. Just need to zoom in on this sheet I've got because I can hardly read the thing. Right. So C, value of the 3 secondary impedances transferred to primary. So what we need to do this analysis is transfer the impedances from the primary secondary side to the primary side, like we did in the example before the Easter break. D, primary current for fully loaded transformer. E, the secondary current under the same conditions as part D. Yeah. And F, the apparent power to the load under these conditions. All right. Keep running out of space, don't we? Okay.
Yep.
So that's what we're going to go through together, step by step. All right. So first of all,
Sorry, can you go back to
yeah,
the
sorry,
other slide?
Ben. Yeah.
The apparent sorry, for F it says the apparent power to load under this what?
Under these conditions, the same conditions as
Oh.
in parts D and E. The situation there is the transformer's rated at 100 kVA, so it's got a full load current. But when you're trying to draw that full load current, you're going to lose. You're going to have losses due to X1 and R1 in each, and X2 and R2 inside. It means you don't actually draw that much current. Do you see what I mean?
Yep.
Yeah.
All right. So the transformer ratio. With the information given, how could I find the transformer ratio?
Well, you've got the you've got the 2 voltages, and you've got the number of turns. No, you haven't.
No, you haven't got the number of turns, but you're right. You've got the voltages, so we can find it from EP over ES. That's 11,000 over 400. I've got 27.5.
Yep.
Yeah.
Yep.
So A, the transformer ratio is 27.5. B, how can I find I2 at full load? Given the information that we've got. Anyone see it? Bearing in mind, if we had the value of the load, that would be easy because we got the voltage. We've got no ohmic value for the load impedance at this stage. But we do know S full load because that's the rating of the transformer. Yeah. There's 100 kVA. We also know that S is equal to I2 times E2. Therefore, I2 is S over E2. Yeah. 100 times 10 to the 3 divided by 400. I've got 250 amps. Am I right?
Hang on, I messed this up. So 100
Yeah, I've got that.
divided by.
And it wants the value of resistance per resistant load.
Yeah.
that
So when you
would
say
cause that.
E2, you've used ES, have you? Yeah.
Yeah, sorry, ES.
I
Yeah.
was going to say, I was trying to work out where I was, and then,
Yeah. Yeah, we haven't calculated E2 yet, have we? Right. And therefore, the full load resistance, the resistor that would draw a full load current is ES over I2, 400 over 250 equals 1.6 ohms. I got.
yeah, 1.6. And so that, yeah, so that is R, but that's essentially Z as well.
Yeah, that's the Z is that, but it's per resistance.
Yeah.
All right, ZR. Okay. Now, part C was transferring the 3 secondary impedances. So that's X2, R2, and the load over to the primary side. So if you can remember, can anyone remember? Let's do, what we're going to do is transfer secondary impedances to primary side. All right, you might find this a little bit confusing for a minute, Roger, because you missed the last session, but I'm sure you'll get it in the end. Okay, we'll start with the load resistor. So RL, remember when we transferred it, we call it RL dash. Yeah. Can anyone remember the formula for doing that?
My memory's getting tested now.
If you can remember it, you'll be the first student who has over Easter. I squared times the resistance as it is on the secondary side. Yeah. So we multiply it to transfer from primary to secondary. We multiply by the transformer ratio squared. So that's 27.5 squared times 1.6. I've got 1210 ohms, but please check.
Yep.
Yeah.
Yeah, talk then.
X2 dash, therefore, is I squared X2. Which is 27.5 squared times 0.03. I'll make that 22.7 ohms. Yep.
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 And then lastly, R2 dash is equal to A squared, sorry, times R2, 27.5 squared times 0.008 equals 6.05 ohms. Yeah. All right, everybody up with that? Can I move on to a new clean slide?
Yep.
Right. So that are the values of those components. So what we've got now, diagram boys, is this. HE BP 11 kV. Yeah. We've got R1, that is 12 ohms. X1, 36 ohms. We've got R2 dash 6.05. We've got X2 dash 22.2, was it?
22.7, I think.
7.
Unless I've got that wrong. Yeah, 22.7.
And we got RL dash here would be and RL dash is 1210. Yeah. Our transformer is over here. Ideal transformer is over there. So we got every component now transferred to the primary side. Yeah. And the current flowing here is equal to I1, but it's also I2 dash. They're the same current because they're transferred. So there's I1 is equal to the I2 transferred to the primary side current. All right. Now part D asks us to find the primary current, the fully loaded transformer. Yeah. So if it's supplied with its nominal primary voltage, so that's what we've done. Got the nominal primary voltage on here. So D. What's the first thing we need to do to be able to find that current flowing? We've got the voltage being applied. We've got a complete series circuit through R1, X1, R2 dash, X2 dash, and RL dash. So what formula would we use to calculate the current?
E over Z.
EP over ZT. So what have we got to find first?
ZT.
ZT. It's got three real parts, R1, R2 dash, and RL dash. So we can get that from R1 plus R2 dash plus RL dash, real part, plus X1 plus X2 dash J ohms. Yep. So we got a complex number situation here. Real parts, resistances, imaginary parts, positive imaginary parts because they're inductors, X1 and X2 dash.
Yeah. So
that's
how come you can just add RL dash into the first two? Because is that not in parallel? Would that not be different, or?
No, it's not in parallel, Robbie. Remember this transformer over here, I didn't really have room to draw it. Okay, has got nothing connected to it anymore because we shifted it over to the primary side. So there's no current flowing in here. So we've got the current flow is all in series around there. Yeah. So we add the three resistive parts together. 12 plus 6.05 plus 1210. And we add the two inductive parts together, 36 and 22.7 J. All right, I make that 1228 plus 58.7 J ohms, and converting that to polar, 1229 ohms, angle 2.73 degrees. But please check.
No. You're a bit ahead of me now, but let me just catch up. Yep, that's what I got.
Okay. Yeah. Everyone happy for me to move on to new page?
Yep.
Yep.
Right. So we can now calculate and say, therefore, I1, which is also equal to I2 dash, the reflected secondary current to the primary, is equal to EP over ZT. That's 11,000 angle 0 degrees divided by 1229 angle 2.75 degrees. Is it 2.73? Sorry.
Yeah.
And I make that 8.95 amps angle minus 2.73 degrees. And we know it's inductive, and therefore the current lag and the voltage is what we would expect. Yeah?
Mm-hmm.
So looking back, how much current we have in the secondary side on full load? Is it 250 amps?
Yeah.
Yeah. And we got primary current of 8.95 to deliver that. Right? It's quite a significant difference. Yeah.
Yep.
Right. So part E said, I can't remember. Secondary current under the same conditions. So what we've got to do now is we know the secondary current transferred to the primary. We know I2 dash is equal to this 8.95 amps angle minus 2.73 degrees. We transfer I2 to the, so we I2 dash, if we knew it in the secondary, is transferred to the I2 transferred the primary as I2 over A. Therefore, I2 is equal to A times I2 dash. Equals 27.5 times 8.95 amps angle minus 2.73 degrees. Angle will stay the same anyway. 246.1 amps angle minus 2.73 degrees. All happy with that?
I thought to work out dash it was A squared times.
When you transfer an impedance as A squared, Ben?
Yeah.
When you transfer the current or voltage, it's just A.
Right. Okay. Right.
So when you're transferring the other way, from secondary to primary, you transfer currents by the secondary current over A, transfer voltages by the secondary voltage times A. So to go back the other way, you just have to rearrange those formulas.
Right. Okay. That's fine.
Yeah. It's transferring the impedance that involves A squared, like we did a little while ago. All right?
Yep. That's fine.
Yep. Okay. Everyone happy? Can I move on?
Yeah, fine.
Yep.
So, F. We can say that the secondary voltage transferred on the primary side can be given by I1 times RL dash. Yeah?
Yep.
We go back to our drawing. We're calculating this voltage here, E2 or ES dash. And then once we calculated it, we can transfer it back. Yeah.
Okay.
So that's 8.95 angle minus 2.73 degrees times RL, which is 1210 angle 0 degrees. And I make that 108 30 volts angle minus 2.73.
Mm-hmm.
Yeah.
Yep.
Now we also know ES dash is equal to I times ES. Therefore, ES is equal to ES dash over A. So that's 108 30 angle minus 2.73 over 27.5. And I make that 394 volts angle minus 2.73. So nominally, when we put 11 kV in, we're supposed to get 400 volts out, but because of the losses, we're only getting 394. Yeah.
Yep.
And therefore, I think the last bit was to find S on S for the secondary under these conditions, wasn't it?
Yeah.
So S is equal to I2 IS, sorry, I2 ES. That is I2 was 8.95, wasn't it? No, that's I1. Go back. I2.
Is the 246 one?
246.1, yeah. ES 394 equals.
Would we not use the angles on this one?
The angles would cancel out.
Oh yeah, yeah, they would. Yeah.
Yeah.
Oh yeah, and yeah, okay, yeah. Yeah.
And the answer to that is because mine seem to have been cut off the page. That should be close to 11,000, close to 100,000, shouldn't it?
96.
Yeah.
96,000 VA.
Yeah.
Yeah.
I got 96.9 kVA.
Yeah.
Yeah. That's near enough. So you know, that's just showing you what the losses. You just calculated the losses in that transformer.
Yeah.
All right. So, is there just one question left on the tutorial sheet now? I think there isn't.
Yeah, I think there is.
Do you want me to put the question sheet back up?
Mm-hmm.
Yes. Yeah.
Yeah.
Yeah, one question left then, yeah. Real transformer. So you're being asked to do, I would believe, more or less what we've just done. 75 kVA, primary voltage 14.4 kV, secondary 230. Got your values. Find the ratio, load current, load resistor, transfer and impedance methods. Find the primary current, secondary current for full load, voltage across the load. That's slightly different, but we'll know it in as the secondary voltage, and the apparent power. Right?
Did you need?
Okay, Lewis. Who's that? No, that's right. I said, what do you reckon to your first foray into online sessions then, Roger?
Again, sorry?
I said, what do you reckon to your first attempt at online sessions?
It's not too bad, is it? It's,
Yeah. Well, I don't think that's gone too bad anyway, considering what we were thrown in at the deep end.
no, I think you just need to get, sometimes you just need to get on with it, really, don't you? So it's absolutely fine.
Yeah, yeah.
So I'm now on part C. Just looking at
Yeah,
the example from before. RL dash, that's the resistance of the load, is it?
yeah,
So that is that Z resistor at the end there. Just because you can see, yeah, I just got a bit confused because you can see X2 and R2, but yeah, I'll put a little thing.
yeah. It's drawn as a resistor, but technically you'd have to say it's an impedance because you're AC.
Yeah.
Yeah. So they're kind of interchangeable. If you're talking about pure resistance, you can interchange R and Z.
Yeah.
But as soon as you combine it with anything reactive, like an inductor or capacitor, then it has to be Z. Yeah.
Yep.
Made up of resistance and XL and XC.